Hello! Today we'll be learning about particle-wave duality, but first we need to know what classical waves and particles are. Particles are extremely small constituents of matter. Waves, no, not that kind, are disturbances that transfer energy through matter or space. So quite simply, particle-wave duality is the concept that all matter exhibit both kinds of behavior in different circumstances. But how does that work? That's a tad more complex. The concept was first mentioned in 1924 with de Broglie's hypothesis, which postulated that all particles, not just massless photons, have a wave-like nature. He generalized the Planck-Einstein relation to this form, relating a particle's momentum to its wavelength. In 1961, Klaus Johnson conducted Young's double-slit experiment with electron particles instead of light waves. According to classical mechanics, the electrons should have formed two strips through the slits. However, they actually formed an interference pattern just like that of diffracted waves, with areas of high and low intensity. This showed the wave nature of massive particles and helped substantiate de Broglie's hypothesis with empirical data. And even when there was only one electron in the slit apparatus at a time, the same interference pattern was formed. Thus, the electron could only be interfering with itself. But when researchers tried to passively detect which slit the electrons traveled through, they reverted to particle behavior. This is known as the observer effect. The mere act of observation forced the electrons to behave differently, collapsing their wave function, a combination of the probabilities of finding the electron in each possible position. This phenomenon was explored in 1935 with the thought experiment of Schrödinger's cat. Erwin Schrödinger stated that if you placed a living cat and an apparatus that has a 50% chance of killing the cat into an isolated system, as long as you don't open the box, the cat is in a superposed quantum state of both dead and alive. This concept is known as the Copenhagen Interpretation, in which a physical system only has indeterminate probabilistic properties until it is observed and forced into possessing definite physical properties. When you open the box, the cat will either be alive or dead, as it cannot be observed in its superposed form. Fun fact, Schrödinger was actually trying to disprove the Copenhagen Interpretation with his cat example, but instead it was widely accepted as part of quantum theory. The uncertainty behind quantum mechanics and particle-wave duality presents a fundamental problem to our understanding of the world. We collect data through observations, and if that itself can change the data we get, what is real, and can it be measured? Can a consistent reality exist when everything is based on probability waves? Is everything dependent upon the observer's perception? Is quantum theory even the right way to define the universe? Finally, I would tell a superposition joke, but I'll keep it in a box for now so it can be funny and not funny at the same time.